All right, welcome everyone. We're going to get started. So welcome back. Hope everyone had a nice fall break. A few reminders before we get going. We do have homework due tonight. So sections I3 and I4 are due tonight. This week is our recitation exam 6 in recitation. So, at your scheduled time, you'll go through the usual process for our exams. Make sure you know ahead of time which follow-up questions from exam 5 that you have to redo. And then make sure you look at our news feed on our course website, because I made some announcements there that are going to be important for the last few weeks. Believe it or not, next week is already the last week of the semester. And this is all on the course website, but for next week, we're going to have our last follow-up exam. So we scheduled that for next Thursday at 6:30 to 7:30. And so that's just going to have all the questions from exams 1 through 6 on it. And any questions that you still have progressing on, you'll be able to retry those again during that exam. So it'll be an hour long next Thursday. So if you absolutely cannot take the exam at that time, please send me an email this week just letting me know. Take a screenshot of your class schedule on your Hub Student Center just so I can see what the conflict is, and we'll go from there. But that's our last follow-up exam is next week, Thursday. That way you have recitation time next week to ask questions, and for anything from this most current exam that we're going to be taking this week. So that's next week. And then we also have, some extravaganzas are coming up. Also next week, I'll be reopening all the old homework assignments for one last chance to finish any remaining problems that you haven't finished. So all the sets will be open for a few days. So, make sure you kind of plan out your time so you can get any remaining problem sets finished up. I'll make an announcement specifically when I will open everything up, but it'll be open for a few days. And then we're also going to have the final exam extravaganza. So basically any question on the final exam that's testing one of our learning outcomes that we've looked at on our recitation exams, if you score a 90% or higher for that question, that can be applied towards your mastery check. So, think of the final exam as sort of one last opportunity to try our recitation exam questions again. So that's really the recitation exam questions. It's just building up for the final exam. And so if you can do it on the final exam, then I will kind of retroactively apply that to the appropriate recitation exam. So again, all of this is I kind of have one big announcement on our course website. So read through it. Let me know if you have any questions, but I just want to mention it again before we get started today. All right. So today we're kind of going into our last theme of the course, and that's sort of to look at what it means conceptually when we talk about integration. So for the first topic here, we're going to see how to find the particular antiderivative of a function given an initial condition, and then see how this relates to the topic of motion in a straight line. So position functions, velocity functions, acceleration. So let's start with an example. We're going to find the particular antiderivative f of the function f prime of x equal to x plus 1 over square root x. So far we've been finding the general antiderivative where we go through our usual integration rules and then we slap on a plus c at the end. Well, here we're given a little bit additional information. we're given this f of 1 equal to 5. And so this is, a lot of times we call this like an initial condition. And what we're going to use this initial condition for is it's going to help us determine what the value of that constant c is. So we kind of looked at this, over the past couple weeks. Every time we do the derivative of a function, we lose a little bit of information. And so we're never able to fully recapture our original function by integrating. There's always that unknown constant that we write at the end. But having this initial condition, this is the extra information that we need to figure out the value for c. And we're going to see how to use this in this example. All right, so we want to figure out the antiderivative of this function. So we're used to this part. So that's step 1. We're going to integrate. So to get our original function, we're going to take the derivative and we're going to integrate it. So we know derivative and integrals sort of cancel each other. They're reverse processes, so they sort of cancel each other out, almost. So that's going to be our first step here. We're given the derivative f prime, and to work backwards, we have to integrate that. So let's go through the process. And we're going to integrate our derivative that we're given. So x plus 1 over square root x. Now, this is, as it's written, we got to do a little bit of work here to get it into a format that we can actually find the antiderivative of. So when I look at this, I see a fraction. And a lot of times with fractions, especially when there's just a single term in the denominator there, we want to try and see if we can do the division first. So that might be something to try. Let's see if we can do this division first. So we're going to split up our fraction here into, give myself a little more room, x over square root x plus 1 over square root x. So we can break that up into two separate fractions. So each term in the numerator becomes its own fraction essentially, and we use the same denominator for each one. All right, so there's our fraction split apart. Still not quite the right format, so we want to see if we can cancel, and eventually we'll rewrite those fractions and root functions with regular exponents. But we got a little bit of canceling we can do first. So x divided by square root x is just square root x. And then we have the plus 1 over square root x. And then finally, we're almost there. Things are looking a little bit better, but we want to get those as power functions. So we're going to rewrite the root signs as 1 over 2, and then we'll use negative exponents to get rid of that one fraction. And you maybe do this some other way. So these are the step, one approach to take. You might do it slightly different, and that's fine. So I would write this as x to the 1/2 plus x to the negative 1/2. Just like that. And we're going to integrate that whole thing. X to the 1/2 plus x to the minus 1/2. So now each of those are power functions. So we can just use our regular power rule now and go find each of those antiderivatives. So x to the 1/2. We do the power rule. Our variable is x. We add 1 to the exponent, which takes us up to 3/2. Take that new exponent, flip it, put it in front, so 2/3. That's the integral of the first term. Then we go to the second term. Our variable is x. Add 1 to the exponent, so that bumps us up to positive 1/2. And then take that new exponent, flip it, put it in front. so we get 2 in front, 2 over 1. And then we're doing an indefinite integral so far, so we use plus c at the end. So on the exam today, or on Thursday, if it's an indefinite integral, remember to include that constant term at the end. All right, so there's f of x. We're almost done. We now need to figure out a value for c, and this is where our initial condition comes in. So we're going to figure out the value for plus c. So we have this we almost have our function f of x. 2/3 x to the 3/2 plus 2x to the 1/2 plus c. And our initial condition, what is it? Let's write it down. Our initial condition was f of 1 is equal to 5. So when we plug x equals 1 into our function, we should get 5 out. So let's see what happens when we do that. Let's plug 1 into what we have for our derivative, or for our antiderivative so far. So we're going to plug 1 into this expression. And when we do that, we get 2/3 times 1 to the 3/2 plus 2 times 1 to the 1/2 plus c. Those powers of 1 are just equal to 1. So what we end up with here is 2/3 plus 2 plus c. So f of 1 is equal to 2/3 plus 2 plus c, and we want this equal to 5. So we're basically going to set these two expressions equal to each other and then solve for c. So we're setting the 2/3 plus 2 plus c, and we're going to set that equal to 5. Both of those are equal to f of 1, and we want them to be the same. So if we do the solution there, what do we get when we solve that equation for c? And we get 7/3. So we figured out the c value. And really the last step then is just to put everything together. So, you know, it always feels good when you get something, you do all this work and you get c is equal to a number and it feels like you're done. We're not quite done. We just need to plug that back into what we have for our function. So we said our function was 2/3 x to the 3/2 plus 2x to the 1/2, and then we figured out our value for c was 7/3. So we just want to make sure we answer the question. The question is, we want to find the function f. And yeah, so really all we're seeing here, to find the particular antiderivative, we go through the same integration process, but then we're just using that extra information that we have to figure out the value for c. Let's try another one. Let's try, well, we're going to do one involving a second derivative. So we're going to find the particular antiderivative f of the function f double prime of x equal to 12x squared plus 6x minus 4. Now here we're looking at a second derivative. So each time we do the derivative, we lose information. So what we're trying to do here is we have original function f, we have f prime, and we have f double prime. So we're given f double prime, and we kind of want to work backwards. So we're going to work backwards. We're going to integrate once to get f prime. And then not quite there. We're going to integrate a second time to get to our original function f. And so each time we have to do that integration, that's one more little piece of information that we need. So that's why we're given two initial conditions here, because we're working back from the second derivative. So each derivative, essentially, that we're trying to undo, we need an initial condition for to get fully back to our particular antiderivative. All right. So let's try this one. So step one, we're going to figure out f prime. So f prime of x is going to be the integral of f double prime of x. So the integration there will cancel out one of the kind of the derivatives there on our second derivative. Let's fill in what we have for our function. It's 12x squared plus 6x minus 4. And just a polynomial, so we just go through our usual term-by-term integration. And when we do this, we get 4x cubed plus 3x squared minus 4x, and then we remember to include our constant term at the end there, plus c. All right, so there's our derivative f prime. We don't want f prime, we want f, so we have to do the integration again. And so what we're going to do to get f is we're going to integrate our derivative. So that derivative we just calculated, f prime, we're going to integrate that now. So let's fill it in. We're going to integrate 4x cubed plus 3x squared minus 4x plus c. We're going to integrate that term by term again. So the antiderivative of 4x cubed is x to the fourth. The antiderivative of 3x squared is x cubed. And then antiderivative of minus 4x is negative 2x squared. And this is where it's important that we remember that constant term at the end, because when we integrate a constant that's by itself, that c, that plus c, we actually attach a variable to it. So when we integrate c, we're going to get cx. So that's important there. Because we actually get, it becomes part of one of our variable terms there. And since we've done a new integration, we found a new antiderivative here. So when we started with f double prime, we did the integration once, and we added some constant c. Well, we've done a new antiderivative, we've done a new integral, so there is conceivably another constant that gets added on. So plus d. So you can call it what you want. Just make sure you don't use plus c again, because we've already used c. So it's usually a good idea to just go down the line in the alphabet. So c, d, or you could use little subscripts. So c1, c2. That's good as well. All right, so we have f, but now we have these two unknown constant terms. So that's where we have to use our initial condition, or two of our initial conditions, to find those constant terms. So that's our last step here. So we're going to find our constants c and d. So let's start with our initial, that initial condition that f of 0 is equal to 4. So we're going to see what happens when we plug in 0 into the function that we have so far. And we're going to compare that to our initial condition, which says we want f of 0 equal to 4. So we're going to go to what we've calculated for f, and we're going to plug 0 into that. So when we plug 0 into that x to the 4th term, we get 0. Plug 0 into the x cubed, we get 0. Plug 0 into the negative 2x squared, we get 0. Plug 0 into the cx term, we get c times 0, which doesn't matter what c is, it's still 0. And then the only thing that conceivably doesn't disappear is that d at the end. So when we plug it in, all of those terms are going to be 0 except that last one. So our last term there is d. And so we have these two kind of values for f of 0, and we want them to be the same, so we set them equal to each other, and we solve as needed. So when we set these equal to each other, we get d equals 4, which, well, that's it. There's no more work there. So that tells us one of the constants. Now let's try the other initial condition, and hopefully this one will let us figure out what c is. So we're going to look at the initial condition. What is it? F of 1 equal to 1. So we want to know what happens to this function when we plug 1 into it. So let's go through. We get 1 to the 4th plus 1 cubed minus 2 plus c plus d. So all of those powers of 1 are just 1. So we're just plugging x equals 1 into f of x, what we have so far. And if we simplify that down, we have 1 plus 1 minus 2. So that just all cancels out. So the 1 plus 1 and the negative 2 cancel, and we're left with c plus d. And so we want these two values to be the same, so we set them equal to each other. When we plugged in, we got c plus d. And from our initial condition, it needs to be equal to 1. And so this gives us another equation that we can then use to solve for c or d. And since we know what d is already, this tells us then that c is equal to 1 minus d, or negative 3. All right, so we found our antiderivative, and then we used both of those initial conditions to figure out c and d. So now we just need to go back to our original function and just kind of, or not our original function, but go back to our antiderivative and just plug everything in. So we had f of x is equal to x to the 4th plus x cubed minus 2x squared. And then it was plus cx, and we know c is equal to negative 3, so we're going to have negative 3x. And then we had plus d before, and we know d is equal to 4. So we're going to fill that in. And there we go. There's our particular antiderivative for this setup. So in order to kind of undo the second derivative, we needed two initial conditions. All right, so next we're going to see how this relates to motion in a straight line. So rectilinear motion. And kind of the three most important functions that we consider for this course are the position function, which just kind of indicates where our object is at time t. So it gives the location from some kind of reference point. So there's always a reference point in mind here. So if we're thinking of like the x or the y-axis, the reference point might be the origin. So the position function tells us where our object is in relation to that reference point. Then we also have the velocity function. A lot of times we call this v of t. And this gives us kind of two pieces of information. It tells us the speed, so how fast the object is moving at time t, but then it also tells us the direction it's moving in. And same thing for acceleration. We have this acceleration function a of t, and it also tells us sort of the rate at which the velocity is changing. So it tells us if our object is speeding up, if it's slowing down, but it also tells us, gives us information about changes in direction at particular times t. So there's always this idea of, there's sort of the numerical value, which is telling us, how fast we're going, or, how fast we're speeding up or slowing down. But then there's also the sign in front of it, which gives us some indication of the direction. So plus or minus, there's a direction there. So we've seen how these functions are related in terms of differentiation. So the velocity function is equal to the derivative of our position function. And then the acceleration is just the derivative of our velocity, which is the second derivative then of our position. So kind of to summarize everything, we have three functions normally that we're considering. And if you take a physics class, you might look at, there's a third derivative that has some significance, and so on and so on. We're not going to be looking at those in this course. And actually, if you integrate the position function, there is some significance to that as well, but we won't be looking at that in this course as well. So really, for motion in a straight line, the three functions that we mostly consider are position, velocity, and acceleration. So we know that to go from position to velocity, we differentiate. So if we have our position function, to get the velocity function, we do the derivative. If we have our velocity function and we want our acceleration, we do the derivative. So we just kind of hop along there. And if we have our position function and we want the acceleration, well, then just do the derivative twice. So we know integration allows us to work backwards for the most part. So if we had acceleration and wanted velocity, well, do the integral. And if we have velocity and we want the position function, do the integral. So we can kind of work back and forth as needed. And as we've seen, when we do the derivative, we lose a little bit of information each time. So if we're trying to work backwards, we need an initial condition then to figure out our velocity function or our position function to find that particular antiderivative. And that's what we're going to see in the examples. Now just a comment here about the units. So when we talk about position, we're using units of length. So in our examples that we're going to look at, meters and feet and things like that. Now when we do the derivative with respect to time, the velocity function is going to have units of length divided by units of time. And then when we do the derivative of that, to get acceleration, we're going to have unit of length divided by unit of time. And then we just divide by another unit of time. So it'll be unit of time squared. So basically, when you differentiate, you divide by a unit of time. And when you integrate, you're multiplying by unit of time. So just kind of to keep in mind if we're talking about these physical examples, you know, what your units are, what your units should be for position, velocity, and acceleration. So position is just a unit of length. Velocity is a unit of length divided by a unit of time. And then acceleration is a unit of length divided by a unit of time divided by a unit of time. So if we were to start with acceleration and work backwards to velocity, we're going to just get rid of one of those divisions by time. All right, so let's try an example. So let's say we're on a rocket ship, and we're going to fire this rocket ship vertically into the air, and the height, or a lot of times we think of height as just the position of the rocket, is the distance measured from the top of the rocket to the launch pad. So let's draw a little diagram. It's good to picture what's going on. So here's the ground, here's our launch pad. And let's draw our little rocket. And it's just going to be shot vertically straight up into the air. So kind of a simplified system here. But just for the sake of an example, we can kind of imagine that as just motion in a straight line. Straight up. And so what we're measuring for position here the height of our rocket is measured from the top of the rocket to the ground. And when we shoot this thing off, it's going to go straight up. All right. So let's see what we're actually given here. So initially, the top of the rocket is 8 meters above the launch pad. And the velocity of the rocket, t seconds after liftoff, is given by the function v of t, which is equal to 6t plus 0.5. And the units here are meters per second. And what we're going to do is we're going to find the height of the rocket at time t. So really what this is asking, we want to find the height of our rocket. This is telling us, or asking us, to find the position function, find s of t. So if we're given the velocity, the way we figure out position is with integration. And so that's what we're going to start with. We're going to integrate to get our position function. So position, or in this case the height of our rocket, is equal to the integral of this velocity function. So 6t plus 0.5. Do the antiderivative. So the antiderivative of 3t is, or the antiderivative of 6t is 3t squared. Spoiled it there. And then the antiderivative of the 0.5, what is that? That's just a constant term by itself. So we multiply our variable with it. So our variable is t. So the antiderivative of 0.5 is 0.5 times t. And then whenever we find an antiderivative, a general antiderivative, plus c at the end. So remember that for the exams. This exam and the final exam, it's little, but as we're seeing, it does have some significance. We are using this plus c term. All right, so there's our general antiderivative. We want to figure out the particular antiderivative. We want to find the position function exactly. And this is where we have to go back and see if we're given any information about an initial condition. So you might have to read through the problem a little bit to see if you can identify what the initial condition is. Sometimes it's a little bit disguised. Here we're kind of tipped off because it starts off with the word initially. But initially it says the top of the rocket is 8 meters above the launch pad. So that's telling us what our initial condition is here. It's telling us that at time 0, the position is equal to 8 meters. So our height is 8 meters. So, if an actual value for time is not specified, and we use wording like initially, we're kind of imagining this all happening starting at time 0, and then, that's when ignition starts and then it launches off. So we're just kind of starting with t equal to 0 in this case. All right. So we have our initial condition. The units are meters. Now we use that initial condition to figure out C, just like we did in the other examples. So let's plug 0 in. So we know our initial condition is S of 0 equal to 8. Let's plug t equals 0 into the function that we have so far. So we're going to go back up to here and plug t equals 0 into that. And what do we get? Well, we get 3 times 0 squared plus 0.5 times 0 plus c. Simplify. Everything times 0 is just 0, so we end up with just c here. So show that step. It's very tempting a lot of times when you're doing the initial condition. I'm plugging in 0, and I'll just get the constant term. Not necessarily. So as we saw in one of the previous examples, sometimes with our initial condition, I think it was the first one, there's other terms there. So you want to show that step of plugging your t value in or your x value in, just like we're doing there. So in this case, all the zeros kind of cancel, and we get S of 0 is equal to C. Then we also know S of 0 is equal to 8, so we want to set these two values equal to each other. And that gives us the equation C is equal to 8. Sometimes there might be more work to do. In this case, that's it. We're done. And so we have enough information now to write down our position function exactly. It's 3t squared plus 0.5t plus 8. And the units here are in meters. All right, so there's our position or our height function here, height above the launch pad. All right, let's try another one. So motion in a straight line. So a lot of times this is, things being thrown up, or, particles moving in a straight line. So you can always picture it happening on either the x-axis or the y-axis. So in this example, a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff, which is 432 feet above the ground. And what we're ultimately going to do in this problem is we're going to find the height of the ball above the ground after t seconds. So we're going to find the position function, essentially. So first, let's kind of picture what's going on in this example. All right, so we're going to do everything in relation to the ground. So that's, if we look at our little pieces of information there, the one says that our ball is kind of thrown upwards. We're on a cliff. Actually, let's draw the cliff here. Here's the cliff. So we're standing on top of that cliff, and we're going to throw the ball up. And we're just kind of just barely leaning over the cliff there. We throw it up, and what's going to happen is the ball is going to go upward, it's going to slow down, and then it's going to fall back down, and it's going to hit the ground right at the base of the cliff there. And so we want to find a function that describes the height of the ball at any time t. So everything's in relation to the ground. So the first thing we want to do once we have a little diagram like that is just kind of look at the information we're given. So what are we given? Well, we're given that our ball is thrown, we're on top of a cliff that's 432 feet above the ground. So that's really describing the initial position of our ball. So at time 0, that's when we throw the ball up. And this is 432 feet. Now, for position, acceleration, and velocity, we need to decide a direction. So everything is being kind of based off of the ground. So that's going to be our reference point. You could do it some other way, but to make things easier, we're going to use the ground as our reference point. And so because our ball is starting above 432 feet above the ground, we're going to say up is the positive direction. So when we look at our position function, we'll think of it as positive 432. So positive meaning it's above the ground, and then 432 is how many feet it's above the ground. So we want to decide on position or on direction. What else are we given? So we're given some other kind of initial condition here, and if we look through it, we're told that the ball is thrown upward with a speed of 48 feet per second. So we're going to use that information, and that's going to tell us what our initial velocity is. Now, velocity has kind of two components. There's the numerical component, which tells us the speed, but then there's also a direction. So we're told that our speed is 48 feet per second, and the ball is thrown upward. So that's our positive direction. So it's going to be positive 48. So if we were standing on our cliff and we were to just throw the ball down towards the ground, well, we would be going not in the positive direction, so we would have used a negative there. But in this case, we're throwing the ball up initially, so that's why we're making the velocity positive 48 instead of negative 48. All right, so that's what we're given. We're given the initial velocity, 48 feet per second, and we're given the initial position, 432 feet above the ground. Now, there's some implicit information that's given here. So we're standing on a cliff on Earth. We're on planet Earth. So there's a little bit more information. And that has to do with Earth's gravity. So Earth's gravity near the surface, we generally assume is constant, particularly for kind of slow-moving objects like this. It's not technically constant, but near the Earth's surface, we can assume gravity is constant. Gravity is technically related to the mass of the objects and the distance of the objects away. So the further you go away from Earth, the smaller the gravity value gets. But if we're right around the Earth's surface, small changes in distance like this aren't going to really affect the value of gravity. So we can assume that gravity is constant. And so gravity is acceleration in this case. And it doesn't matter what happens in regard to time. We're just throwing this ball up a little bit and then it falls back down. So we're assuming gravity is constant throughout that whole time. So if we're using, since we're using feet, the general value for gravity here is approximately 32 feet per second per second. If we were using meters, then this would be 9.8 meters per second per second. So we're using feet, so we'll use the one constant there. Now, like with velocity, there's kind of the numerical component, but then there's also a direction component with it. So we started by throwing our ball up, so it was going up. It was going in the positive distance direction, the positive displacement, up. Earth's gravity wants to pull everything down to the ground, so gravity is working in the opposite direction. So it's pointing down. So we're going to make the acceleration function, or a of t here, we're going to make it negative. So it's going to be negative 32. All right. So that's kind of all of the pieces of information that we need. And when we look at this, again, just a reminder, the negative here is because gravity is in the opposite direction. So it's acting in the opposite direction. And we want to think of that negative 32, that's a constant function. So no matter what time is, gravity is always going to be the same near the Earth's surface, in this case, negative 32. So when we actually go to figure out our height function, we're going to integrate our acceleration a couple times. All right, so let's start with our acceleration. So our acceleration function is just a constant, negative 32. And we know that to get the position, we have to first get the velocity. Then once we have the velocity, we're going to get the position. So if we start with the acceleration, we're going to integrate it once, and that'll give us velocity. So let's integrate negative 32 times dt. So we're integrating with respect to time. Find the antiderivative of that. It's negative 32t plus some constant c. And we want to figure out that constant c, so this is where our initial conditions come in. So we also had v of 0 was equal to positive 48, and s of 0 was equal to positive 432. So we're going to use both of those at some point, hopefully. So we have kind of the general idea of what our velocity function is, but we want to find the particular value. So we want to find plus c using that initial condition. So we're going to take 0, plug it into what we have so far for our velocity. So we get negative 32 times 0 plus c. And we want those two values to be equal, so we set them equal to each other. And when we do that, we get the equation c is equal to 48, because 0 times negative 32 is just 0. So that happens to tell us what c is. We don't always get that lucky. Sometimes there's a little bit of work there that we have to do in order to solve for the constant term. But in this case, we get exactly what c is. So now let's use that. Let's rewrite our velocity function with that value for c plugged in. So negative 32t plus 48. So we don't want just the velocity function, we want the height function. We want our position. So we're going to integrate that. We're going to integrate one more time. And so to get our position, that'll be the integral of our velocity function. So let's integrate negative 32t plus 48. And if you want, you don't have to solve for c right away. You could just do the integration all at once, and then once you once you have that, then go back and use the initial conditions to figure out c and d. But we had one of our initial conditions was v of 0. Might as well just find it as we're going along. All right. So let's do the antiderivative. Antiderivative of negative 32t would be negative 16t squared. Antiderivative of 48 is 48t. And then we're doing an antiderivative, so we have to add on some arbitrary constant at the end. We've already used c, so let's call this one d. And now we just need to figure out what d is. And here we're going to use our other initial condition. So our initial condition for position was s of 0 equal to 432. So this number in here, that tells us what value to plug in for t. So if it was s of 1 equal to 432, then we'd be plugging 1 in. But because it's s of 0, we're going to plug 0 in. So when we plug 0 in, we get negative 16 times 0 squared, so 0, plus 48 times 0, so 0, plus d. And we want this equal to our initial condition value. So we just set these two equal to each other and see what we get. So in this case, we get lucky again, and we get exactly that d is equal to 432. Again, sometimes when you set those two equal to each other, there might be a little bit of work you have to do in order to solve for your constant term, but here, there's not much. We get d is equal to 432. And now we just update our function. So we know s of t is negative 16t squared plus 48t. And now we just update that constant term, so plus 42. And the units are going to be in feet. So there's our position function. All right, so just kind of practicing, kind of integrating as needed, and then using the initial condition to figure out the value for our arbitrary constant. Now let's play some games with our velocity and acceleration function. So we can answer some kind of additional, now that we have our formula for s of t, we found that it was negative 16t squared plus 48t plus 432. We can use that then to answer kind of questions about our system here. So, for instance, when does the ball reach its maximum height? All right, so here's our cliff again, and the ball is thrown upward. And when you throw something upward, it goes up and up and up, and then eventually it slows down and then stops, and then it starts falling back down, and it picks up speed as it falls back. So when it hits the high point, it hangs there for a minute. So if you throw a ball up into the air and you watch it, you'll see it kind of just almost be moving in slow motion for a split second. It kind of slows down right at its max height. And so what happens at its max height, this is where the velocity is equal to 0. So our max height happens for a simple system like this, where the ball goes up and then comes back down. It happens where the velocity is equal to 0. So that's one of our critical numbers for our function s. So let's calculate the derivative. So v of t is equal to s prime of t. So let's do the derivative. We get negative 32t plus 48. And so to figure out the max height, this is really where the derivative s prime is equal to 0. It's one of our critical numbers. So as soon as you see those words maximum, minimum, well, max height, s describes the height, so we want to do the derivative. We set the derivative equal to 0. It's negative 32t plus 48. And then you just solve that for t. So in this case, we get 48 over 32, which is 1.5. And our units of time here are seconds. So it reaches its max height after 1.5 seconds. So what happens is it hits that height, and then it changes direction, and it starts moving in the opposite direction. All in a straight line. And it falls, and then eventually we kind of leaned over the cliff there. So, we're living dangerous, and we throw the ball up, and it comes back, and then we get out of the way, and then it falls and it hits the ground. And when it hits the ground, what happens there is the height is equal to 0. So when the ball hits the ground, since we're measuring our position in relation to the ground, our position function is going to be 0 there. So for part C, when does the ball hit the ground? Well, that's when our position function is equal to 0. And that's what we want to find. We want to set our position function equal to 0 and solve for t. So let's take it. Negative 16t squared plus 48t plus 432. We set that equal to 0, and then we're going to solve that for t. Now we have all kinds of techniques at our disposal to kind of solve this. This one looks a little bit complicated, so you could try factoring it. That's normally what you try first. If that doesn't work, if you can't figure out how to factor it, this is a quadratic, so the quadratic formula will always work. So let's use the quadratic formula. And so we get t equal to negative 48 plus or minus the square root of 48 squared minus 4 times negative 16 times 432 all over 2 times negative 16. And that plus or minus there in the middle is telling us conceivably that we have two different time values where the ball hits the ground. So let's just simplify this. And it does simplify down a little bit. We get -3 plus or minus 3 times the square root of 13 over -2. And really, that plus or minus is an indication that we have two possible values for t here. So there's the negative. So we have -3 minus 3 square root 13 over -2. But then there's the positive part there. -3 plus 3 square root 13 over -2. And both of these are valid solutions for this equation. Both of these are correct solutions for that equation. But there's more context here. So we're talking about an actual problem where we throw a ball up into the air and, it falls back down. We kind of start the process off at t equals 0. So it doesn't really make any sense to think about negative time. So for this problem and for this question to make sense, we're really only considering positive t values. And so we have to throw out any negative time values that we get here. It's technically a correct mathematical solution, but it doesn't answer the question. So -3 plus 3 times square root 13 over -2, that would have been a negative value for time. So the ball can't hit the ground before we even throw it. And so that means the other time value is when the ball hits the ground. So approximately about 6.9 seconds after we throw it. All right. So that'll kind of do it for one of our first conceptual learning outcomes here for applying and investigating integration. So I'm just looking at the questions. So what we're doing today, just to be specific, what we're doing today is not going to be on exam 6. This might be on the final exam, things like this, but it won't be on recitation exam 6 this week. All right. Let's go to another application of integration. We're going to see how definite integrals are related to area. So in this learning outcome, which we'll start today, we're going to use definite integrals and maybe a little bit of geometry to calculate the net area and the total area between a curve and the x-axis. All right, so let's just first introduce our terminology. So we say that the phrase area under the curve, well, when we use that phrase, what we mean is we're talking about the region that's bounded above by the graph of our function f of x. So let's look at a little diagram here. Here's f of x, and we're going to see how to calculate the area under that curve. So the top of our region, do a little better than that, is going to be bounded above by our function f. So that's going to give us the top of our region. It's going to be bounded below by the x-axis. So that's going to give us the bottom part of our region. So right on the x-axis there. And then the actual limits of integration we see are going to give us the left and the right side of our region. So the left is going to be a vertical line at x equals a, and our region will be bounded on the right with a vertical line at x equals b. So if we were looking at, say, maybe something like this. So it's the area under the curve but above the x-axis. So when we say area under the curve, what we mean is it's that region that's sandwiched in between our function and the x-axis. And for this interpretation, we're going to assume a few things about our function f of x. It needs to be continuous on the interval a to b. So jumps and breaks in our graph, we need to be a little bit careful with that. And then also for this interpretation, our graph needs to be non-negative. So what we mean by non-negative is it has to be greater than or equal to 0. Or if we want to think graphically, the graph of our function never goes below the x-axis. And so what we're going to first see is for functions that are continuous and non-negative, so they're above the x-axis, we're going to see how to calculate the area of this shaded region. And let's try an example. Nope. Do an example in a second. We're going to do just to really stress. So we're going to see next time, we'll see that there's kind of two slightly different area calculations that we're going to be doing, depending on if our function is above the x-axis or below the x-axis. So for our discussion right now, we're only considering functions that are non-negative, so that they're above the x-axis on our interval. So if we have a continuous function that's also non-negative, it's above the x-axis on the interval from a to b, then the area of that shaded region, the area under the graph, is equal to the definite integral. So it's just the integral of f of x from a to b. And so really kind of reframing what we've seen with definite integrals in terms of area is really going to be helpful in a lot of situations. So this is going to be kind of the correct context for how to visualize what we're calculating with definite integrals. We're really calculating the area under the curve. And again, really to stress here, for this interpretation, we need our function to be non-negative. So this interpretation only works if our function is non-negative. It's above the x-axis. So important enough to just kind of stress this again. When we do the definite integral, if our function is above the x-axis, then that definite integral is just the area under the graph. All right, so let's try an example. Let's compute the area under the curve f of x equal to 3 over x plus e to the x from x equals 1 to x equals 2. So first thing we note is this function, and we've graphed it below there, but 3 over x is continuous except at x equals 0, but we're only in between 1 and 2, so x equals 0 is not a problem. And for positive x values, this function is positive. So we just want to note here, before we get going with our area calculation, our function is continuous. And non-negative, so positive essentially. On this closed interval from 1 to 2. And we can see that in the graph. So in between x equals 1 and x equals 2, our function, there's no jumps or breaks, and the function is above the x-axis. So here's our function f of x. And we're interested in finding the area below, under the curve, from x equals 1 to x equals 2. And by area below the curve, we mean above the x-axis, though. So we're going to find the area of this shaded region. So let's set up our area. The area is going to equal the integral from 1 to 2 of our function. And our function is 3 over x plus e to the x. And we've been doing these problems now for a couple weeks, so this shouldn't be too bad. We're just calculating a definite integral. So let's get the antiderivative of that first term, which is 3 over x. And if you don't see how to do that one right away, a lot of times it helps to kind of break the fraction apart. So maybe it helps to rewrite this as 3 times 1 over x. And when we integrate that, the 3 is a constant multiple. And so we really just want the antiderivative of that 1 over x term. And we know what that is. It's kind of a special one. It's the natural log of absolute value x. So that's the antiderivative of 3 over x. Then we want to do the antiderivative of e to the x. And exponential functions are nice. They're their own antiderivative. So the antiderivative of e to the x is just e to the x. And we're doing a definite integral here, so we're going to evaluate this entire thing from x equals 1 to x equals 2. So we have our antiderivative. Now we just need to plug in. So top number goes in first. We get 3 times natural log 2 plus e squared. I like to put a nice big set of parentheses around that whole value from when I plug the top number in. Then we subtract and we plug in our lower number, which is x equals 1. So we get 3 times natural log 1 plus e raised to the power 1. Again, it helps if you use parentheses, but don't overuse parentheses. So I like to kind of set up the framework. Top terms minus the bottom terms. And then you just kind of plug everything in. And that's it. That's the value of our definite integral. Now there is a little bit of simplifying we can do here. Natural log of 1 is just 0. So we can simplify this down. It's just 3 times the natural log of 2 plus e squared minus e. And so that's the area of that shaded region. And if you wanted to, you could get a decimal value for that, but I would just leave it as the exact value there. All right. So we'll stop there for today. We'll pick this up more on Thursday, so we'll look at kind of what the definite integral means in terms of area in general. So we'll look at a few more examples along this. And then we'll probably get into the next learning outcome, which will have to do with distance. So we'll see that the definite integral, not only is it related to area, but it's also in some context related to distance. So if we have an object that's moving in a straight line, the integral of our velocity function, we'll see, is related to distance traveled. All right, so we'll stop there. Reminder, we have our recitation exam 6 this week in recitation. When you do, make sure you have your Zoom device set up so that we can see you. So we need to see your face, your writing surface, and your computer screen. So make sure you test it out. And specifically for the final exam, we're going to be very strict on how your Zoom device is positioned. So make sure you have that set up for this exam correctly. So we need to be able to see your face, your writing surface, and your computer screen. All right. So good luck, and we'll see everyone on Thursday. Bye-bye.